This is problem 96 from chapter 17, and there's a picture for the problem here. In problem 96, we read the spool has a mass of 100 kilograms and a radius of gyration of 0.3 meters. If the coefficients of static and kinetic friction are 0.2 for static and 0.15 for kinetic, determine the angular acceleration of the spool if the force P here is 50 newtons. So I have three things that I can do in this problem. I can do the sum of the forces in the x direction is equal to the mass times the x component of the acceleration of the mass center, sum of the forces in the y direction. But the acceleration of the mass center in the y direction is 0, so the mass center is staying at the same height. And then I can sum up the moments. I'm going to sum up the moments about point G. That's equal to the moment of inertia about point G times the angular acceleration. So the radius of gyration that they gave me, that can be used to find the moment of inertia about point G. And that would be equation 17.5. So moment of inertia about point G is equal to the mass, which is 100, times the radius of gyration, which is 0.3. squared, and that gives me 9. Okay, so I have to do a free body diagram, and I know I have a force of gravity acting downwards. That's m times g. I have a normal force acting upward. I have this force P here. I also have a force of friction, but this is tricky because I'm not told whether or not the spool is rolling without slipping. If the spool is slipping, then that is kinetic friction, and if it's not slipping, then it's static friction. Also, it's not clear what direction the force of friction is acting in. So because this force P is above the mass center, you're going to cause the spool to rotate as well as to move in this direction. So you have angular acceleration like this just because of point P, and you also have acceleration this way. So depending on the point where the spool is touching the ground, this point could be moving this way relative to the ground or this way relative to the ground if there was no friction. So I don't know whether it's static friction or kinetic friction, and I'm not sure what direction it's acting in, so I'm going to assume it's acting in the positive x direction, and if I get something negative for the force of friction, then that was wrong. And I'm just going to call it F sub F since I don't even know whether it's kinetic friction or static friction. Okay, here let's look at the sum of the forces in the y direction, and because the mass center is not moving in the y direction, we can say the normal force is equal to m times g. The mass is 100, so that's 981 for the normal force. Now we can look at the sum of the forces in the x direction. So that's my force P of 50 newtons plus force of friction is equal to mass of 100 kilograms times the x component of the acceleration of the mass center. So I have two unknowns in this equation. I can then look at the sum of the moments, and I have this force P, which would cause acceleration in the... Actually, let's not do that. Let's say I'm going to sum up the moments and have this be the positive direction when I sum up the moments. So I know the angular acceleration is in this direction, so let's just call this the positive direction for this problem. So that force P is being applied at a distance of, this is 250 millimeters from point G, so that's 0.25 times force P is 50. Force of friction would cause rotation in this direction. That's for this problem, that's the negative direction, so that's minus. This distance here is 400 millimeters. That's the outer radius, so that's 0.4 times the force of friction. That's equal to my moment of inertia of 9 times the angular acceleration. Okay, now I'm in trouble. I have two equations. Let's call this equation 1 We'll call this equation 2. I also know what the normal force is, but that's only useful to me if I know the force of friction is kinetic friction, or if I know that I'm at the maximum value for the force of static friction, and there's no reason to think that I'm at the maximum value for the force of static friction. So now we're going to make an assumption, and we're going to see if that assumption's true. So assume that we have rolling without slipping, and then we'll see what happens. So if we are rolling without slipping, then at the point where the wheel is touching the ground, that is our instantaneous center of zero velocity, and the x component of the acceleration of the mass center is equal to the distance from the instantaneous center to point G, that's 0.4 meters, times the angular acceleration if we are rolling without slipping. Okay, so if I make that assumption, then for equation 1, I get 50 plus the force of friction is equal to 100 times 0.4 times the angular acceleration. So that would be 40 times the angular acceleration. Okay, and then I have equation 2 here, and equation 2 has now the same two unknowns as what I have here, so I can solve for the force of friction. And when I do that, I get 2 for the force of friction, and because it's positive, it means my assumption here was correct, and friction is indeed going to the right. So I get 2 newtons, and if I use that and go back to either this equation, let's just go back to this equation here to find the angular acceleration. The angular acceleration is 1.30 radians per second squared. Okay, but that was assuming rolling without slipping, so I need to make sure that it is actually rolling without slipping. So friction needs to be 2 newtons to the right in order to have rolling without slipping. And I found the normal force. I have the coefficient of static friction, so the maximum value for the force of static friction is 0.2 times 981, and that is 196.2, and 2 newtons is definitely less than 196.2 newtons, so it is indeed rolling without slipping. Okay, and so because it's rolling without slipping, we can say, what were we looking for here? Angular acceleration is 1.3 radians per second squared. And if it was not rolling without slipping, then we would have kinetic friction instead of static friction, and you can find the force of kinetic friction by doing coefficient of kinetic friction times normal force. That concludes problem 96.